My name is Kate Grier, and I'm a graduate student at The Ohio State University. Today I am here to discuss our recent paper entitled The Structure of the Broadline Region, Reconstructed Velocity Delay Maps. In this coffee brief, I will address some of the main results of this paper. One of the continuing mysteries in the study of active galactic nuclei, or AGN, is the structure and kinematics of the Broadline region. It is generally accepted that AGN are powered by supermassive black holes, and the broad emission lines seen in Type 1 AGN are the result of photoionization of gas in the Broadline region. It is impossible to study the structure of the Broadline region directly because it is very small in angular size on the sky and is spatially unresolvable in nearly all galaxies. To learn about the structure of the Broadline region, we must rely on reverberation mapping techniques or the microlensing of gravitationally lensed quasars. Reverberation techniques use time variability observed in the AGN continuum emission and the subsequent response of the gas in the Broadline region. By monitoring the AGN over a period of time, we can determine the distance of the emitting gas from the central source by measuring the time delay between variations in the continuum and the response of the emission lines. This time delay is due to the light travel time between the continuum source and the Broadline region. A main goal of reverberation mapping is to recover the velocity delay map, which shows the response of the emitting gas as a function of this time delay and the line-of-sight velocity of the gas. The velocity delay map describes exactly how the continuum flux variations give rise to variations in the Broadline region flux, and therefore contains information about the Broadline region geometry and kinematics. Most previous reverberation studies have been limited to measuring the mean time delay for various emission lines, which allows us to measure the mean radius of the Broadline region. However, this offers very little information about the detailed structure of the Broadline region. In this work, we present velocity-resolved reverberation results for 5 active galactic nuclei observed in our 2010 reverberation campaign. In particular, we recovered 4 velocity delay maps for these objects using the maximum entropy method as implemented in the program MEMECHO. Figure 13 in our paper shows simulated velocity delay maps for 4 simple models for possible Broadline region structures to compare with our actual recovered velocity delay maps. You can see that infalling gas shows longer lags toward the blue end of the line and shorter lags toward the red. The models for the inclined Keplerian disk and the thick spherical shell show symmetric bell-shaped profiles. Our 4 actually recovered velocity delay maps each look quite different, but each shows similar signatures that are reminiscent of those seen in our models. Figure 12 in our paper shows false-color velocity delay maps actually recovered for these objects. The different colors represent different emission lines in each object, with red representing H-beta, green representing H-gamma, and blue representing helium-2. For 3C120, the Balmer lines show kinematic signatures consistent with either an inclined disk or spherical shells and infalling gas, but the helium-2 emission line is suggestive only of inflow. The Balmer lines in Markarian 335, Markarian 1501, and PG2130 plus 099 show signs of infalling gas, but the helium-2 emission in Markarian 335 has a chevron shape that is consistent with an inclined disk. In nearly all cases, we see evidence for radial stratification of the Broadline region, as the maps show H-gamma and helium-2 emission responses at progressively smaller radii than H-beta. These maps constitute a large increase in the number of objects for which we have resolved velocity delay maps, and the maps from Markarian 335 and 3C120 are 2 of the most clearly defined velocity delay maps to date. All of the signatures seen in our recovered velocity delay maps suggest the gravitational influence of the black hole. As gravitationally dominated motion is a key assumption of reverberation mapping, our results strongly support the reliability of reverberation-based black hole mass measurements. If you'd like more details on this study, please take a look at our paper, which was posted on astro-ph today. Detailed modeling of our most well-defined velocity delay maps, as well as a complete discussion of the implications, will be presented in a future work, so please stay tuned.